Welcome back to Science Fact Tech, where we delve into the forefront of science and technology. Today we're exploring one of the most promising and exciting fields in energy research: fusion energy. If you've ever wondered about the potential of harnessing the power of the stars, you're in for a treat. Let's dive into the progress made in fusion energy, its challenges, and what the future holds. Section 1. What is fusion energy? First, let's understand what fusion energy is. Fusion is the process that powers our sun and other stars, and it occurs when two light atomic nuclei collide with enough energy to overcome their electrostatic repulsion and fuse together, forming a heavier nucleus. This fusion process releases an enormous amount of energy, mainly in the form of heat and light. For instance, in the sun, hydrogen nuclei fuse to form helium, releasing energy that radiates out into space and sustains life on Earth. What makes fusion particularly appealing as an energy source is its potential to provide a near-limitless supply of energy. The primary fuels for fusion, such as deuterium and tritium, can be derived from seawater and lithium, making them abundant and sustainable. Unlike fossil fuels, fusion produces no greenhouse gases and generates minimal, long-lived radioactive waste, positioning it as a clean alternative in the global energy landscape. Section 2. Why fusion energy? Why is fusion energy so crucial in today's world? As we face escalating climate change and the urgent need to transition away from fossil fuels, the demand for sustainable energy sources has never been greater. Fusion energy stands out for several compelling reasons. First and foremost, it has the potential to provide a nearly limitless source of energy. Unlike fossil fuels, which are finite and contribute to environmental degradation, fusion uses isotopes of hydrogen, deuterium and tritium, as fuel, both of which are abundant and readily available. Additionally, fusion energy produces minimal environmental impact. It generates no greenhouse gases during operation, significantly reducing its carbon footprint. Moreover, the radioactive waste produced is considerably less hazardous than that from nuclear fission, with a much shorter half-life, making it easier to manage. Furthermore, fusion power plants can operate continuously, unlike solar or wind energy, which are dependent on weather conditions. This reliability means that fusion could play a pivotal role in achieving energy security and stability. As we strive for a cleaner and more sustainable future, harnessing the power of fusion energy could be the key to meeting global energy demands while protecting our planet. Section 3. Historical context. The quest for fusion energy has a rich history that dates back to the mid-20th century. The journey began in the 1950s when scientists first started exploring the potential of nuclear fusion for energy production. One of the earliest efforts was Project Matterhorn, initiated at the California Institute of Technology, which aimed to create a controlled fusion reaction. Simultaneously, the Soviet Union was developing the tokamak, a magnetic confinement device that would become a cornerstone of fusion research. The first successful fusion reaction in a laboratory setting occurred in 1952 at the University of California, Berkeley, where researchers achieved fusion using a stellarator design. These early experiments laid the groundwork for modern fusion research, leading to the establishment of various programs and facilities dedicated to understanding and harnessing fusion. As we reflect on these milestones, it's clear that the path to fusion energy has been paved with innovation, collaboration, and a relentless pursuit of knowledge. Section 4. Major fusion projects. Today, several significant fusion projects are underway around the globe, each contributing to our understanding of fusion energy and moving us closer to practical applications. One of the most ambitious initiatives is the International Thermonuclear Experimental Reactor, or ITER, located in Cataract, France. This large-scale international collaboration involves 35 nations, including the European Union, the United States, Russia, China, Japan, South Korea, and India. ITER aims to demonstrate the feasibility of fusion as a large-scale and carbon-free source of energy by producing 10 times more energy than it consumes, a critical milestone that could pave the way for commercial fusion power plants. Using a tokamak design, ITER employs powerful magnetic fields to confine hot plasma, which is essential for achieving the high temperatures and pressures required for fusion. The project has faced numerous challenges and delays, but its first plasma is expected to be achieved in the coming years, marking a significant step forward in the quest for fusion energy. Another major project is the National Ignition Facility, NIF, in the United States, which focuses on inertial confinement fusion. NIF uses an array of powerful lasers to compress and heat tiny pellets of fusion fuel, achieving conditions necessary for fusion reactions. In 2021, NIF made headlines for achieving a record energy yield during an experiment, igniting excitement in the scientific community about the potential for inertial confinement as a viable path to fusion energy. In addition to these large-scale projects, private companies like Helion Energy and TAE Technologies are also making strides in fusion research, exploring innovative methods and technologies to accelerate the timeline for commercial fusion energy. These diverse approaches and collaborative efforts highlight the global commitment to unlocking the potential of fusion energy as a sustainable solution for our future energy needs. Section 5. The National Ignition Facility. The National Ignition Facility, or NIF, located at Lawrence Livermore National Laboratory in California, represents a significant advancement in the pursuit of fusion energy through inertial confinement. Established in the early 2000s, NIF employs an impressive array of 192 powerful lasers that focus on a tiny pellet of fusion fuel, typically a mix of deuterium and tritium. The goal is to compress and heat this pellet to extreme conditions, millions of degrees Celsius, sufficient for initiating a fusion reaction. In December 2021, NIF made headlines when it achieved a record energy output from a fusion reaction, marking a historic milestone in fusion research. This experiment demonstrated that the facility could produce energy in a controlled setting, bringing scientists closer to achieving ignition, where the fusion reaction produces more energy than is consumed in the process. NIF not only aims to advance fusion energy, but also plays a crucial role in national security by supporting the Stockpile Stewardship Program, ensuring the safety and reliability of the U.S. nuclear arsenal. As NIF continues to conduct groundbreaking experiments, its contributions could significantly influence the future of fusion energy and its potential as a sustainable power source. Section 6. Recent breakthroughs. Recent years have witnessed exciting breakthroughs in fusion energy research, reflecting the growing momentum in this field. One of the most significant developments occurred in December 2021 when the National Ignition Facility, NIF, achieved a landmark milestone by generating a record amount of energy from a fusion reaction. This experiment marked a pivotal moment as it demonstrated the feasibility of achieving energy gain in a laboratory setting, a crucial step toward the goal of ignition. The NIF's success has reinvigorated interest and investment in fusion energy, showcasing the potential for practical applications in the near future. In addition to the advancements at NIF, private companies are also making impressive strides in fusion technology. For instance, Helion Energy announced that it successfully achieved a major milestone with its plasma generator, demonstrating the ability to produce consistent energy output. Their approach focuses on using magnetic fields to confine plasma, offering a potentially more efficient and cost-effective method of achieving fusion. Another noteworthy player is TAE Technologies, which has been developing a unique form of magnetic confinement fusion called field-reversed configuration. TAE has made significant progress in optimizing its reactor design, with the goal of achieving net energy gain in the coming years. Moreover, global collaboration in fusion research is on the rise, with countries sharing knowledge and resources to accelerate advancements. Projects like ITER and various national laboratories are united in their mission to unlock the secrets of fusion energy. These recent breakthroughs and collaborative efforts signal a promising future for fusion energy, as scientists and engineers work diligently to overcome the challenges and bring this clean, limitless energy source closer to reality. Section 7. Challenges facing fusion energy. Despite the significant progress made in fusion energy research, several formidable challenges still stand in the way of realizing its full potential. One of the primary hurdles is achieving and maintaining the extreme conditions necessary for a sustained fusion reaction. Fusion requires temperatures exceeding 100 million degrees Celsius, over 7 times hotter than the core of the sun. At these temperatures, matter exists in a plasma state where electrons are stripped from atoms. Containing this plasma in a stable form is crucial for enabling the fusion process, and it requires sophisticated magnetic confinement systems, such as those used in tokamak designs. Another challenge is the need for efficient and sustainable fuel cycles. While deuterium is abundant in seawater, tritium is radioactive and must be bred within the reactor itself. Developing a reliable mechanism for breeding tritium while managing the reactor's overall efficiency is essential for long-term fusion viability. Additionally, maintaining the stability of the plasma over extended periods is a complex task, as small disturbances can lead to instabilities that disrupt the fusion process. Funding and international collaboration also play a critical role in overcoming these challenges. Fusion research is an expensive endeavor, requiring significant investment in infrastructure, technology, and talent. Moreover, the collaborative nature of projects like ITER involves navigating the complexities of international agreements and funding commitments. Any delays or budget overruns can impede progress. Furthermore, public perception and acceptance of fusion energy are vital. While many view fusion as a promising solution to the energy crisis, concerns about safety, waste management, and the timeline for commercialization can create skepticism. Educating the public about the benefits and safety of fusion technology is essential to garnering support. In summary, while fusion energy holds immense promise, addressing these challenges is vital for turning this dream into a practical reality. Continued research, innovation, and collaboration will be key to unlocking the full potential of fusion energy as a sustainable and clean power source for the future. Section 8. The future of fusion energy. The future of fusion energy is filled with potential and promise, as scientists and engineers work tirelessly to overcome the challenges that have historically hindered its development. As we look ahead, several key trends and advancements indicate that fusion could play a transformative role in the global energy landscape. First, technological innovations continue to emerge, enhancing our ability to achieve and maintain the necessary conditions for fusion. Advances in materials science, for instance, are leading to the development of more resilient materials that can withstand the extreme temperatures and neutron bombardment within fusion reactors. This progress is crucial for constructing reactors that can operate efficiently and safely over extended periods. Moreover, the increasing participation of private companies in fusion research is injecting fresh ideas and competition into the field. Startups like Helion Energy, TAE Technologies, and others are exploring alternative approaches to fusion that may offer quicker pathways to commercialization. Their innovative methods, combined with established research facilities, create a diverse ecosystem that accelerates progress. International collaboration is also expected to play a pivotal role in the future of fusion energy. Projects like ITER exemplify how countries can pool resources and expertise to tackle complex challenges. As more nations recognize the urgency of addressing climate change, the push for clean, sustainable energy solutions will likely strengthen global partnerships in fusion research. Public and governmental support for fusion energy is growing, driven by the increasing demand for clean energy sources. As awareness of climate issues escalates, policymakers are more inclined to invest in and promote research in fusion technology. In conclusion, the future of fusion energy appears brighter than ever. With ongoing advancements, collaborative efforts, and a growing commitment to sustainability, fusion has the potential to become a cornerstone of global energy production, providing a clean, abundant, and reliable energy source for generations to come. Section 9. Public interest in education. Public interest and education are crucial components in advancing the field of fusion energy. As the scientific community makes strides in fusion research, it is essential to communicate these developments to the public effectively. Raising awareness about the potential benefits of fusion, such as its sustainability, safety, and abundance, can foster greater support for research initiatives and funding. Educational programs play a vital role in demystifying fusion energy and inspiring the next generation of scientists and engineers. By integrating fusion science into school curriculums and hosting outreach events, institutions can engage students and spark interest in STEM fields. These initiatives not only cultivate a knowledgeable workforce, but also empower communities to understand the significance of fusion as a viable energy solution. Moreover, public forums and discussions can help address concerns and misconceptions about fusion technology. By providing transparent information and involving community voices in the conversation, stakeholders can build trust and encourage a collaborative approach to energy innovation. In summary, fostering public interest and enhancing education around fusion energy
Section 10
are essential to ensuring a successful development and implementation.
Fusion energy
Ultimately
represents a
leading
beacon
to
of
a more
hope
informed
in our
society
quest for
ready to
sustainable
embrace
and
this
clean energy
transformative
sources.
As we confront the pressing challenges of climate change, dwindling fossil fuel reserves, and the urgent need for reliable energy, the potential of fusion as a safe, virtually limitless power source becomes increasingly significant. The advancements achieved in recent years, particularly through major projects like ITER and the National Ignition Facility, highlight the progress made in understanding and harnessing the power of fusion. These breakthroughs not only pave the way for future experiments, but also foster a renewed sense of optimism within the scientific community and among policymakers. The commitment of various nations and private enterprises to invest in fusion research underscores the global recognition of its potential. However, it is essential to acknowledge the challenges that still lie ahead. Achieving sustained fusion reactions, developing efficient fuel cycles, and ensuring the safety and reliability of fusion reactors are critical hurdles that require ongoing research and innovation. Furthermore, fostering public support and understanding of fusion technology will be crucial in building momentum behind this promising energy source. As we move forward, the collaborative efforts of governments, research institutions, and private companies will be vital in overcoming these barriers. By prioritizing fusion energy research and supporting international cooperation, we can accelerate the development and deployment of fusion technology. Ultimately, the successful realization of fusion energy could revolutionize the global energy landscape, providing a clean, abundant, and sustainable power source that meets the needs of future generations. With continued dedication and investment, the dream of fusion energy could soon transition from theory to reality, shaping a brighter and more sustainable future for our planet. Thank you for joining us on this exciting journey into the world of fusion energy. We hope you're as inspired as we are by the incredible advancements and potential this technology holds for our future. Imagine a world powered by clean, limitless energy. It's within our reach, but we want to hear from you. What are your thoughts on fusion energy? Do you believe it can be the game changer we need for a sustainable future? Share your ideas and questions in the comments below, and let's spark a conversation. If you enjoyed this video, don't forget to like, subscribe, and hit that notification bell so you never miss an update. Together, we can explore more groundbreaking technologies and innovations that could transform our planet. Stay curious and keep pushing for a brighter, greener tomorrow.